Now, I will mention if you're not feeling comfortable with this warm up and you're still thinking, oh man, I don't get this, that's okay. We're going to spend days on this and we're going to keep building and building your skills. So don't give up. Um, and I probably was a little bit too cruel to start. Notice here I put r prime. Well, wait a minute. R prime of t, isn't that the same as dr dt? And the answer is yes. So sometimes I do that to trick you guys. Sometimes we do that just so you guys can think about it. Now, what did Mr. Waffler show, which I think is really important for us, even though we haven't really talked about this yet? Um, if I'm going to get rid of derivatives, I need to use that integral symbol. That was that funky looking S. But before I can do that, I need to just take this dt and I need to multiply it so it's over on the other side. All right, so I'm kind of doing too much work here, but this is officially what it should look like. And I'm doing my best to make my t's not look like my pluses. So this entire thing is basically saying that this is the derivative with respect to t. That's what we got. So how did we get rid of a derivative? We had to use that elongated s, which is called the integral symbol. And that's our symbol for undoing a derivative. So we can always sneak a 1 in here. If there isn't something there, you can always put a 1. And then I'm thinking about, okay, well, whose derivative gave me 1? Well, that's just a variable. That would be r. Right? The derivative of r is 1. And that's one thing that's nice is you can always check your answer. If you say this is the antiderivative, take the derivative of it. Do I get back where I started from? So then I've got 3 pieces. These are all just separate facts. This one might be the hardest. But whose derivative gives me e to the 7t? Well, anytime you have base e, it's going to be exactly the same thing. But if I say that's my answer, then I'm checking this, right? The derivative of e to the 7t is e to the 7t, but then I would have to times by a chain rule here. And that's the part that we want to be careful with. If I did that, if this was my answer, then I would have a 7 right out in front. I want to compensate for the fact that that 7 would go there. So I'm going to put a 1/7 out in front. And this might take more time to develop, but that's officially what the antiderivative of e to the 7t is. Okay, let's check the next piece. Right, the next piece, this one's kind of tricky. A lot of students overlook this. Whose derivative gives me 1 over t? Well, I'm going to think of this. If it was 1 over t, and I write it like this is a power rule, which says I should add 1 to get the antiderivative. But if I do that, I get t to the 0, which is 1, and that doesn't help me. So this is a special fact that we will spend a lot more time on, but its antiderivative is the natural log of the absolute value of t. Right? Because remember, if we take the derivative of ln, it's 1 over t. So I'm taking the derivative of my answer to get back to where I started. So just be careful with that 1 over t. That can trick people. And then the last piece is whose derivative gives me secant tangent, secant squared, and that is just tangent. You can put the t in parentheses, it doesn't really matter. But the one thing we have to be careful with is that once you write your antiderivative, you have to put a plus c. Remember that plus c is a constant, and that constant could be like having a plus 3 at the end or a plus 5. The derivative of a constant goes away. And Mr. Waffler talked about that in the video on Wednesday. So you can go back and watch it if you didn't get it. All right, notice that's a general solution. Why is it considered a general solution? Because any value will work. It's general because we just put a plus c at the end. we're going to look at the next example was the particular solution. And that is the fact that you're going to do the same work we just did, except for when you get to this point, you're going to actually plug in, and in this case, it would be a t and an r value. But you're going to plug in a value to find the value of c, and then that'll be your particular solution. Okay? You can think of particular as like specific solution. All right, so let's try this one again. And the very first thing I'm going to do is I need to split up this dx dt. Now be careful with x. A lot of students think x is always the independent variable. In this case, it's not. It's dependent upon t. So t is the independent variable. So I'm going to move the dt over to the other side. And I also, because I'm really used to it, I'm going to rewrite this part right here. I don't like anything other than 1 over t. I don't like the t to the negative, to the 2 down there. So I'm going to write it as negative t to the negative 2 power. So just remember that's a better way to think of fractions. And then we got 6t minus 4. And remember, we moved the dt over to this side with multiplication. Okay, so now, how do I get rid of the derivative of x and the derivative of t? We use that special symbol called an integral. And now we're taking antiderivatives. Well, remember, if it's just dx, you can always put a 1 there. And the whose derivative gives me 1? It's whatever variable it is. So if this was like a dh, then the antiderivative of 1 would be h, but it's a dx, so it's just x. All right, so here's how I like to do these power rule ones. And I'll show you with kind of all of these. These aren't anything special, but I know that if I'm going to do the antiderivative, I need to add 1 up top. Okay, so that's going to give me t to the negative 1. Now, notice, we had the negative there already, right? And if you want, you can think of that as a negative 1. So let's just say I had a negative 1 there. But if I put a negative 1 up top, I should always divide by that. And the reason why is, look at what happens. A negative and a negative turn into a positive, and I'm really left with t to the negative 1, a positive t to the negative 1. Now, here's my answer. If I take the derivative of that, do I get back where I started, the original black piece right here? Yeah, the negative 1 comes down. That's where this negative 1 comes from. And then I take 1 away, so it turns into a negative 2. So this is the step I would do in my head, and I would get it to be right here. Well, let's take that same work with this one. Remember, this is t to the first power. So I've got 6t to the first power. Well, what do I need to do? I need to add 1 to it. So if I have that, I've got 6t squared. But if this turns into 2 up top, then when I'm checking my answer, if the 2 would times by the 6, so it would be accidentally doubled. So I got to compensate for that. And one way I like to think of it is if I put a 2 in the exponent, I'm going to divide by 2. And what does that do? That gives me 6 divided by 2 is 3. So 3t squared. That's my answer. In our head, let's do the derivative. The derivative of 3t squared, the 2 comes down, 2 times 3 is 6, and then I take 1 away, gives me t to the first power. Okay. And then the last part, this is just a constant, and we know the derivative of a constant means there had to be a variable attached to it. So it's just negative 4t. If I check, the derivative of negative 4t is negative 4. And then I want to put plus c. Now, I like to circle this. This isn't my answer, right? This is the general solution. That's what we did in number 1. Now, I want to use this right here. Now, we have to be careful. This is written as dx dt, right? Which another way to write this is the spot 1, 5. And I purposely did this so maybe it tricked you. T is the independent variable, so T is the first part, and then X is the output. So what do? We take our general solution and we plug in the 1 and the 5. Right? So X is 5, and then wherever I see a T, I'm going to plug in 1. So there's a T here, T here, T here. And notice, by using this specific point, it's making this a particular solution. It's given us the point that's basically help us find the value of C, that constant that makes this equation go through the point 1 comma 5. And usually they're friendlier points. I picked 1 because 1 to any power is 1. And then this adds up to 4 minus 4 is 0. So I end up finding C equals 5. So it's just substitution. I hope you're really good at substitution. And finally, my final answer is to take the general solution that we had before and then just add the C value to it. Okay? We found C equals 5, so we literally just plug it right back in. And this is the particular solution. You can kind of think of this. Notice I left this space. If you really want to, you could call this x of t, because that's just another function notation. Or you could have just said x. It didn't matter if it has a t there or if it just says x. Okay, we are going to do a lot more with this. So I just wanted to kind of check to see, were you paying attention in the video, and can you handle a little more challenging pieces? What we're going to do next is a Kahoot game. Yeah, a couple of questions. We'll talk about grades at the end of the hour, quick. So, but if you have a question, you can email me. We're going to do a really quick Kahoot. This should take about 6 or 7 minutes. And what I'd like you to do is join in really quick. And it's a basic antiderivative piece, and it's nothing tricky. It's just basically reversing the derivative. So if you have the app, open it up on your phone. Here's the code, or go to www.kahoot.it. Are connected, but you might not see the connection yet. I'm put a reminder up here. This is more for me to tell you guys. Just remember the AP exam is due January 31st. Mr. Saifong sent an email out to everyone that has the explanations of how to pay, where to pay, what to do. Quick reminder, it's $50 per exam unless you qualify for free and reduced lunch, and then it's $10 per exam. You do get completely refunded if you do not take the test. So if you're not certain yet whether or not you're going to take the AP test, pay for the test now before the 31st, and then you can always opt out of it and you'll get that money refunded. Now, if you take the test, let's say you open, if we're doing it online for some reason, and you just click on it, you open it, then they're going to consider that you take it and you don't get refunded. So we'll talk more about that, but if you're not sure, pay for the test, and you can always get refunded if you don't take it. All right, so our goal today is to go over a couple of sections here, and it's going to sound like a lot, and it is. We've got a pretty heavy day here. Um, but we're estimating finite sums, which is also called Riemann sums. And it's a fancy way of saying, what's the area under the curve? Okay, and this is all connected. In a couple of days, you're going to see how everything is connected here and it's all built up. Um, but for right now, I just want you to write the title, and then I'm going to show you what we mean by area of rectangles, area of trapezoids, and how it's connected to that antiderivative and the integral that we just talked about. So go ahead and write the title. I have some things that we're going to be doing, but I just want to share with you quickly what we're doing and how it looks visually. So you kind of have this nice visual appearance before we start going over the problems. So don't write any of this stuff that I have down here. We have things called LRAM, which is the LRAM stands for left rectangular approximation method. And when I see that, what it means is we're going to draw rectangles from the x-axis up to the points. And when we talk about the left endpoint, we're going to be using the left side. So let me just show you what a left rectangular approximation would look like. Let's say that I got a curve. So I have a function, and if I graph that curve, it might look like this. Okay? So it goes like that. And then I want to draw rectangles at the 4 points, but I want to use the left-handed side. So notice the left refers to the left point. So if I draw a rectangle, I'm going to come up, and I'm going to go over and here. Okay? So there's a question just quick in the chat. How do we pay for the AP exam? There is a check your school email. Mr. Sefong or Miss Trevette sent the email about AP, how to pay for the AP test. And there's a sign up. It's all electronic, and you can do it. If you can't find it, talk to me during my office hours, and I'll get you the link. Okay, so notice what I did. I drew a rectangle, and its endpoint is based off of the left side of the rectangle. So then if I go to the next point, I want to draw a rectangle based off of its left-hand side. And then same thing here. So here's another point. So I'm going to draw a rectangle from the left side. And notice I've got 1, 2, 3 rectangles. And I can find the area of a rectangle by doing length times width, length times width, length times width. But the width is the distance between the points, and the height is the output of the left-handed side. So we're going to refer to that in a little bit. Well, what would a right rectangular approximation method be? Or we call those RRAMs. Well, here's the way my brain works, is if I want to have a rectangle, and I want the right side of it to be the point on the curve. Okay, let's say I have basically that same function I had before. Watch what happens when I draw my right rectangles in. Well, now I'm only going to use the part of the curve that's on the interval. So I can't draw a rectangle over here because I don't know where it would stop. So that means I'm going to actually start this direction, and I'm going to go to use the right end to draw that. So notice that's the first point that I would use, because if I try to draw a rectangle over here, I don't know where it stops. So we kind of ignore the first point on a right rectangular approximation, kind of like I ignored the last point on the left rectangular one. But notice if I go from this point here, this is on the right side of the rectangle. And then here's a tricky one, right? I want to use this point and I want to draw a rectangle, but there isn't one, so it's a flat. But I still have 1, 2, and you can think of this as a rectangle with a 0 area. So those are two things we're going to be looking at today, is the right and left rectangular approximation methods. We also have something called a trapezoid, and I'm sorry, midpoint. The trapezoid is the next one. The midpoint one is definitely more unique. And if I had that same function, what I would have to do for the midpoint is I want to be what's the middle outcome between these two. So I actually have to select my own value. So notice how my green points are just the middle values between those red points. And then I'm going to construct my rectangle using that. Oops, I messed that one up. Hold on. So I want to create my intervals between these points. So I'm going to go from here to here. And then I'm going to go, and let's say this one is just a little bit higher. Notice my intervals end at the red dots. And then I have this one that will go from here to here. But what do I have? I still have three rectangles. And I want to find the area of those, which is length times width. So when I'm calculating the area, we just think length times width. Well, notice the height on this one is the output of each left point. The height on this rectangle is the output for each of the right lengths. I should have actually got rid of, not this one. I didn't want to circle that one. It's this one, this one, and this one. And then the midpoint heights, those are the outputs of the midpoint values, right? So I do length. The length is always the distance between the red points, but the heights are the outputs of the points that you want to focus on. So I know that probably doesn't make a ton of sense right now, which is completely fine. Let's talk about a problem here, and I'll show you how this is set up. Have your calculator available as well, because I'll give you a hint on some of these problems to make them easier. Okay, so let's read this just so we know what it's asking. And by the way, these problems came from Delta Math, and that's what your homework is going to be tonight. And we're going to basically do the exact same types of problems you're going to experience. So we are evaluating Riemann sums. That's a fancy way of saying the right-handed, left-handed, or midpoint rectangle approximations, given an equation. So let f be defined by the function f of x, and you don't have to write this part. I'll show you what to write down here. Okay, so f of x is 2 to the power of x. We want 5 subintervals of equal length. That's the important part. So they're telling me what to divide this up into. And then they want me to use the right Riemann sum. Okay, so I'm thinking that is my, right away when I read that, I'm thinking I want the endpoints to be on the right-hand side. Okay? Now, look at what they have here. Notice what's given. 2x. That's the function. So I'm going to plug that into my calculator. That's the equation or function. And then I've got my interval with some numbers up on top and bottom. So think of this as your start, and think of this point as the end. Okay, so what I'd like you to write, just to start off with here, is, and I'll rewrite it here, but draw the integral. Ooh. And let's put the start point and the end point, and let's write the function. And then dx. Now, There is a very, very strong connection to what we did in the Kahoot to this 2 to the power of x. Whose derivative gives me 2 to the power of x? We don't really know that yet. We'll get there, but that's not our concern right now. Okay? What I want to do is I want to come up with a table. Okay? So we know in a table, we got inputs and outputs. And I want 5 intervals of equal length. Well, that's the first thing I need to do is figure out what am I going to go by? If I have a start at 3, and then I have the end at 5.5, and I want 5 equal intervals. And my calculator will help me generate a lot of this, which is really helpful. But it says find the interval width. Well, to do that, anytime you want to find your interval width, take your n value minus your start value, and then divide by the number of intervals that we have. Okay. Um, I guess I didn't have to put a 5 right in there right away. I could have done that here, but we know what the end is. I want to end at 5.5, and we know what the start is at 3, and then I want 5 equal subintervals. So if we do that, we end up with 2.5 over 5, or 0.5. And this is the width of each interval. Now, if I was doing this, I wouldn't show this work, right? I guess you don't need to. I would just do that in my calculator or do it in my head. But that means that I'm going to go up 0.5. So the next point is 3.5. And then I've got 4. I might space this out a little bit more just because I'm not sure. I think these numbers are going to be a little bigger than I want. This just leaves me some room. So 3.5, 4, 4.5, and then 5. Okay. Now, we need to figure out the outputs of those, which you don't technically need a calculator for. I mean, if I plug 3 in here, 2 to the third power, we can figure that out, right? If x is 3 and I plug 3 in, 2 to the third power, 2 times 2 is 4, times 2 is 8. And then if I did that for 4, 2 to the fourth power is 16. If I did it for, oh, that's why I'm missing a number. Sorry. I went 5, and then I'd end at 5.5. There we go. So those numbers were easy. I just plugged in 4, 5. The 0.5s, I don't really know them perfectly in my head. You might be able to figure them out, but I want to show you something on your calculator anyways. A question said, why did I use 5 for the subintervals? So it says they told me I needed to use 5 subintervals of equal length. So anytime you want to find the interval width, you take the ending spot and the starting spot and subtract them. So 5.5 minus 3. And then why did we divide by 5? Because they told me they want 5 subintervals. If they said they wanted 4 subintervals, then I'd divide by 4. If they want 3, I'd divide by 3, and so on. Okay, so let me show you this really quick. What I want to do is I want to graph, well, actually I don't want to graph, I want the table of this function 2 to the power of x. Okay, so I hit y equals, and I'm pretty sure students are comfortable with getting a table, right? You plug in the function 2 to the power of x, and I get my table. What you might not be familiar with is how do I change the table set? So watch this very carefully here. Let me see if I can zoom in a little bit. It might be too far. Okay, so here's what I'm going to do. Go second window, which is the table set, and that tells you where you want your table to start from. Well, I want to start at 3, right? That was the starting part of our integral, the lower end. And then this delta table, that tells me my change. Well, that's the subinterval, right? We figured out each interval has to be 0.05 width of a width. So change your table start to 3 and change your change in table, delta table, is at 0.5. Now I will mention that this is good for this problem. If you ever have another table, you want it just to go up by ones, then you're going to have to go back and change this to a 1 to help you out. And we might do that later on. But now, go back to your table. Second table, and look at what you have. You have the output at 3, 3.5, 4, 4.5, 5, and 5.5. You have everything that we need. And then your calculator rounds it to 3 decimals for you, which is good. And we're okay using that for now. Okay, so I'm just going to take those values that I got from my table, and I'm going to put them here, but I'll also just record them in the spot. So this was 11.314, 22.627, and 45.25. Now, my goal is to kind of teach this to you so you don't have to graph and spend a long time doing this, because you could, if we were doing this on a regular time period, in person, we would actually plot these points and I'd create a graph. I don't know if you want to create this graph. I'm going to do it very quickly. And I'm going to kind of put a little break in this graph and say, you know what? X was 3, 3.5, 4, 4.5, 5, and 5.5. Okay? Now, this is where the math teacher in me doesn't love it, but we're going to go with it. If I go over 3 up 8, I'm just going to randomly put 8 right here. There's my first point on the graph. And then I'm going to go over 3.5 up 11 something, which I'm not going to label it. I mean, some students like to do this and just put it right next to that dot. I don't want to make a really accurate graph because the graph isn't that important. Okay, but then I'll go over 4 up 16. Well, if this was 8, if I go double that, that's about 16. So maybe I'll just write the values right above each one of those. And then 4.5 was 22 something, so that's just a little bit higher. 5 was 32, which is double this length. So I'll put 32 right there. And then 45 something would be definitely higher than 32. Okay. So I'm just going to make this a different color so we can see those points. All right, well now what we want to do is I want to do the right Riemann sum. So I need to draw right rectangles for each one of these points. So the dot that I'm concerned with has to be on the right side of the rectangle, which means if I'm doing the right rectangular approximation, I can't go and draw a rectangle here because I don't know where to stop, right? So it has to be between the intervals. And here's where I think you're going to see if you have a table, this is much better, okay? You can do all this work without drawing the graph, and eventually we're going to. So watch what happens. I'm between 3 and 3.5. Well, where is the right side of that? It's right here. So I'm going to use the output of 11.43 as my first rectangle. All right, so I'm going to go here, and notice how I go over to the right and down. It's like we're almost ignoring the first point. Okay? Now, I need to find the area of this. Well, what is the area? The area of this first triangle is a width of 0.5, right? And a height of whatever the output was. And then I'm literally just going to use my calculator. Amari, I'll get to your question in a little bit. And I'm literally just going to multiply those together and get my area for the very first rectangle. So 5.657. Okay? There's the area of this first rectangle. Now I need to do the rectangle between 3.5 and 4, but I want the right rectangle, so I want to use the output on the right-hand side. Well, watch what happens here. In my table, I could technically draw that same rectangle, right? And I could put it here, and that tells me my output is 16. And we know the width anyways, so you really don't need a graph. I hope you're starting to see that this is kind of a waste of time. But then I have to find the area for this one. And its area is the width of 0.5. Notice all the widths will always be 0.5. That's why we found that here. And then the height of the rectangle is the output at 4. It's just 16. And that's a friendly one. Half of 16 is 8. And then we're going to just keep on going. So my next one, I want to find the interval or the rectangle between 4 and 4.5, focusing on the right-hand side. Well, notice the right-hand side has the output of 22.627. So hopefully you're saying, well, I'm going to just take the width, which is the x's, times the height, which is the y. So I want that in blue. All right. Now here's where it gets kind of cluttered, and I don't love this for showing all this work. So I'm going to try to scoot this over. The area of this rectangle is a width of 0.5 times the height, which is 22.627. And multiply those together. And then we've just got a couple more to do. Okay, so then I have to find the rectangle between 4.5 and 5. So I'm going to use the right endpoint. And if I find the area of that one, it's 0.5, 0.5 times the output, which is 32. And then we know that that output is 16. And you're just going to keep going until you're done and you've used all the intervals in the table. So then I've got from 5 to 5.5. Well, that's our last area has a 0.5 or a width. And then the height is the output of the last one, which was 45.255. Green. It's not cooperating. There we go. 20. Try this again. 22.6275. Okay. So, what does this mean? We want to approximate the area under the curve of this function. So, what do? We are going to take the area of 1, 2, 3, 4, 5. Notice we wanted 5 subintervals, therefore I have 5 rectangles, and I just want to take their areas and add them all up. And I should be careful, this is an approximation, so I'm going to put a rough equals to sign. And then I'm just going to take all those green numbers and add them together. And assuming that I added everything correctly, the area under this curve is 63.598. Now again, that's an approximation, right? So we got to be careful. Okay, so let's look at this. This is just a lot of work to start. How can I do this faster and save more time? Well, look at what we have. If you create a table, doesn't the table really show the exact same thing that the graph does? So if I draw a rectangle between the intervals and I want the right side, its width is the x values, its height is the output on the right side. So what if I wanted to do the left side of this? Well, then I would have to use the left endpoint. So I would use an 8 instead of 11.314 for the first triangle. Okay, and then so on. So I'm going to show you the next examples. We're going to try to do this without a graph and save a whole lot more time. And that's the ultimate goal, because these problems can be kind of annoying. All right, and we're going to do another one where we need the interval, so we'll show you that in a second. Actually, you know what? Let's do this. Grab your calculator really quick. And how did we get this table set? Everybody go second window. And then because we don't know what our next function is going to be, let's just change it back to normal. So I'd start at 0. And then instead of doing your table set at 0.5, let's just change that to 1. because that's a normal graph. If my interval width was like 1.5, then I would change it to 1.5 or something else. But now it's just back to normal. And that's how you set your table setup, is just second window. Okay, so let's look at a couple more problems. Let's do this one. Now you'll notice something different with this problem. I don't want you to write, actually don't write anything but the table right here. But notice now they say, we don't know what the function is. We don't know what f of x is, so I can't use my calculator. However, they already give me the table, which is great. The other thing they're saying is we want to use the left Riemann sum. And I'm going to do this without a graph. Right? That's the goal. So what I'd like you to write is draw the table. And we're going to do this in a couple of steps here. And by the way, I'm going to model the work that you would absolutely need to show to earn full credit on a problem like this for an AP test. So we have our table, and we've got x values that go from 3 to 15. And sometimes the table alone can tell you what the interval width is, but we should really just confirm that just like we did on the other one. So what do we want to do? With the interval width, I want to take the starting point and the ending point, and I want to subtract them. Oops. I want to subtract the end minus the start, and then we're going to divide by however many subintervals we want. So I get 12 over 5. If that divides out, I believe that's 0.5. Oh, no, not even close. Oh, this one's interesting. I'll show you this in a second. If we find the interval width, okay, notice it's 2.4, but my table doesn't go up by 2.4s. It goes up different lengths or different widths, which is completely fine. This would be for equal subinterval widths. But we don't need, it doesn't say equal. Notice how it says just 5 intervals, and they are given in the table. So we actually didn't need to do this part for this problem. Okay? And the whole reason why is it didn't say equal. It just says 5 intervals. So hopefully you drew your table. And let's draw the rectangles that would be between these. So what would I have? I'd have a rectangle here between 3 and 6. I would have a rectangle between 6 and 9, 9 and 11, 11 and 13, 13 and 15. And how many rectangles do I have? 1, 2, 3, 4, 5. Those are my 5 rectangles. But now I want the left Riemann sum. So my brain thinks like this. When I see the left Riemann sum, that word left Riemann sum tells me I want my outputs to be on the left-hand side. So I'm going to put little dots on those left sides of those triangles. And now our job is to find the area of them. So let's look. I'm going to use the output of 24 right here. That's how high this length will be. So if you want to draw it, this is a 24 by, and what's the distance between 3 and 6? Well, 6 minus 3 is 3. So the area of this first rectangle is going to be the width times the output of the left-hand side. If you want to think of it as there's the rectangle number 1. Okay. Now again, I'm showing the minimum work right here. You don't have to technically draw these in, but I recommend it. And we knew that this didn't work because they weren't equal interval widths. So now let's go to the triangle 2. Well, what is the width between 6 and 9? It's 3. And what is the height using the left endpoint? The height is 12. So I'm going to take my width of 3 times my height of 12. That will give me the area of rectangle 2. And then we're just going to keep on going for the 3 other rectangles. So you do have to be careful because they might switch the width up. What's the width between 11 and 9? Well, 11 minus 9 is 2. Notice that's a different width than the other ones. And then the height on the left-hand side is 10. So I have a width of 2 and a height of 10, and that will give me the area for rectangle number 3. And I'll do the same thing with 4. The distance between 13 and 11 is 2. And since we're using the left endpoint, its height is 6. So my width times my height is the area of rectangle 4. And the last one, the difference between 15 and 13, that's a width of 2, and then the height is indicated by the left endpoint 10. That's the area of rectangle 5. And then it's literally just multiplying all together and adding it, or sorry, multiplying each piece and then adding it all together. And then just add them all up. So what is the work that you need to show if this was an AP test? I need to see all of this stuff right here. I don't need to see anything else. You don't have to interact with the table, but I recommend it. So if you don't have a table, then you're going to have to use your calculator and generate the table. If you have the table, then it's really quick. Okay, I want to show you a couple of things here just so you guys can get an understanding. And it's a visual don't write these, but what is the difference between a left ram and a right ram if the function is increasing or decreasing? Look at this just quick graphically. See how this graph here, all of the values, this function is increasing and all the values for the left endpoints are below? This would be considered an underestimation because I'm focusing on the left-hand side rectangles and the function is increasing. So I know that this value is definitely less than what the actual area under the curve would be. Well, look at if I take the same function, but now I do the right endpoints. Okay, well, these right endpoints would produce a higher value because we're taking the area and some of that area is above the curve. So this would be considered an overestimation. Okay, now we didn't do the midpoint one yet. I'm going to show you that next. But look at the middle point here. What if we took the middle point? The middle point is actually closer to an actual value than the left and right. So if we're looking for an actual, the best possible way to do it, right now we would say the midpoint one would be better than the left and right. Okay? But what would ultimately be the best way to do this if I wanted to find the area under that full curve? If we increase the amount of rectangles we take, right? If I just kept doing more and more rectangles and the intervals would be smaller, the more rectangles I can get, the more exact I would get to finding the exact area underneath the curve, which is evaluating the interval. I'm going to skip that. So we have 5 minutes left. I want to show you this part right here. And don't write this one. Let me just show you quick what it would be. So notice the directions are basically the same. We start at 1 and we go to 13. But this time we're looking for the midpoint Riemann sums using 4 intervals. So when I see that 4, that means I need to have 4 rectangles. All right. Well, look at all this. If I go and I made a box after each one, I would have 1, 2, 3, 4, 5, 6, 7, 8 rectangles. I want 4. So what we're going to do is we're going to go from 1 to 4. There's my first rectangle. And then I'm going to go from 4 to 7, and then 7 to 10, and 10 to 13. And now I've got 1, 2, 3, 4 rectangles. We can determine the width between them, but what is the height? The height now is the midpoint. It's not the left, it's not the right. We're using the midpoint value. Okay, so let me show you quick how I would do this problem. I would set up the integral, and I would say it's approximately equal to the area of this first rectangle. So its width, 4 minus 1 is 3. And then the height, because I'm using the midpoint, is the middle value, which is 22. And then I would add that to the next one. Well, what's the difference between 4 and 7? That's 3. And its height is the middle value, which is 10. And then I go to the next one. The difference between 10 and 7 is 3. And its height is the middle point at 15. And then I would go the difference between 10 and 13. So this time they actually all have the intervals 3 with a width of 3, which is great. But its midpoint is 20. And then I'm going to save time. You guys can multiply that, add it up, and you'll get the estimated area under the curve for the midpoint. Okay, I wasn't sure if we were going to have time for this, which is completely fine. Next week on Monday, we're going to do trapezoids. Trapezoids are a little bit different. They're more challenging. And we'll talk about some increasing, decreasing. I wasn't sure how far we get, so a lot of this we're going to do next week. Um, I do want you to know the quiz from last week. So I did two things. I looked back, and I don't know if you guys remember the very first quiz that we had in AP Classroom. It was titled 5.1. There was an error with the way that it was written, and it was the first time we tried it. And I decided that if you just attempted it and turned in the work, you got 10 out of 10. And then I decided, you know what? It just didn't go great. And some people were missing it, some people didn't turn in the work, and it was kind of affecting our grade. So I actually ended up taking that quiz and I just gave everybody 10 out of 10. So it's basically no longer in the back of our mind. It's taken care of. Okay. Now, the quiz from last week on related rates is graded. If you did not take that, you need to do that. But that quiz is graded. It was out of 12 points in AP Classroom, but if you submitted your work to Schoology, like we talked about, that was worth 8 points. So in our Schoology gradebook, it's worth 20 total points. You got 8 points for the work. I wrote teacher comments in AP Classroom. So if you got it wrong or if I took off a point, you can go through and look at it as well as any of the multiple choice questions. They have it's designed where you can look at why the option you chose was wrong and why the other one is correct. So please do that. If you want to earn full points back, email your corrections to me with anything that you got wrong. All right, here's the last thing. We have a Delta Math homework, and we did not get to 6.11. I thought we were going to do as much as you can, and we're going to continue this on Monday. So maybe I don't want you to not do it. Do as much as you can. And we did not get to anything with trapezoids. So if you come across a trapezoid one, maybe skip it for now. Okay, but everything else you should be able to do. All right, that's all I have. I'll be in my office hours if anybody needs help. Have a great day.